thanks. Yeah, this is, it's a quote from a panel discussion at the École Normale Supérieure at a meeting that Michael Wright helped organize. I wrote down the quote when it was said, but I didn't write down who said it. And later on, when I checked, both of them said, well, I could have said it, but I don't remember if I'm the one. They had talked about it for a while. They agreed right there on the stage, but both of them just said, I don't know if it was me, but you can say it was me if you want to. So it's a nice moment to remember Pierre and draw better. Good think about it. But why? I don't know. Anyway. Oh, yes. Now the thing is, Grothendieck certainly used universe and topos and schemes. No question whether he used them. Actually, there is some question online whether he used universes, but this comes of not having read what he wrote, because he did. So, and I do not mean to suggest that these were equally important topics to him. They're certainly not equally important topics to him. It's not about that. Yeah, I mean, he considered topos and schemes both. For one thing, he considered them inseparable. You could not really understand either one without the other. I had planned to expand on the idea of using an idea versus believing in it. I was going to use these, I mean, 60 or 70 hours of tape recordings of Grothendieck in 1973. This is really crazy, wonderful stuff. He's speaking in English with a, to my ear, strong German accent. And I suspect that he learned English while living in France, but he learned it from German speakers. So, so he got it with a German accent. But 2 weeks ago, I had to give up that plan. I had to give up that whole opposition of using versus believing, at least in Grothendieck's case. Because I read this from Barry Mazur. Oh, it doesn't say Barry. Oh, yeah, no, okay. It says Barry Mazur in the quote. Rivka Galchen in her New Yorker article. Spectral sequences weren't even seen as a subject on its own 2 feet. Barry Mazur, a mathematician at Harvard who was friends with Grothendieck in the 1960s, told me. It was more of a technique, but Grothendieck didn't approach anything as a mere technique. I didn't even bother approaching it if it was a mere technique. For one thing, if it's just a technique, you couldn't get better than Serre already was at it, right? There's no improvement to offer if it's just a technique. And Grothendieck will learn it from Serre. I mean, okay, even that's a little inaccurate. According to Grothendieck himself, he failed to learn it from Serre, and so he learned it from himself and then wrote to Serre. Here, Barry is taking Grothendieck's own 1950s view of what the Tohoku paper was about. It was about explaining spectral sequences in the 1950s. This is how he writes to Serre. He says, I have overcome my fear of spectral sequences. I had a fear of spectral sequences too. Because I found a delightful special case. Well, a special case that is virtually the general case. He comes up with what's called the Grothendieck spectral sequence for a composite of 2 functors. If you have 2 functors that are, you're interested in their derived functors to calculate some cohomology. You're going to approximate that by forming what's called a spectral sequence, which is a huge calculational device. It's infinitely many quadrant infinite graphs, networks of objects. And you're interested in about 12 of those objects. The truth is, you're going to be able to get to 6 of them on page 1, 3 of them on page 2, and 3 of them on page 3. But you have this whole infinite array of them. And he's going to come up with a version of that. Now, later, the Tohoku paper it turned out to provide exactly the tools of Topos cohomology. Grothendieck comments on this in Rokolte Samai. It wasn't just pretty much the tools. It wasn't that I had established what I needed. It was that if I had been writing an exposition, I mean, these aren't his words, but if he had been writing an exposition of Topos cohomology it would have looked like 1/4 of the Tohoku paper. I mean, not everything was relevant, but it was right there. So universes, I have been going to say, well, he saw universes, they're just a technique to control the size of diagrams, is what I was going to say. But Barry's right. Grothendieck wouldn't have written about them if they were just a technique. He certainly wouldn't have written a 4-page introduction of his own and commissioned a 45-page discussion by Père Samuel. No, he does that because it's more than that. And what he'll say in the Buffalo tapes in 1973, he'll say, I think there's mathematics behind all of this. And he's talking about the use of universes. I feel guilty in a way leaving behind the topic of schemes and topos. These are wonderful topics. There's a lot to say about them. And I have in other things, and other people here have. But I just got caught up on this. What is the mathematics behind universes? In the Tohoku paper, it was to get injective resolutions. You have, say, groups, and you want to calculate cohomology of some sequence of groups, and it would help if every group could be embedded in one that's called injective, which, if we're talking just about abelian groups, it means divisible. It means whenever some element exists, you can divide it by 3 or 19 or 47 or whatever you want. I mean, obviously you can't. If you got an element of Z mod 6, you in general can't divide it by 2, but so that's not an injective, but it's a technical construction that's going to be used all over cohomology. And he gives a general theory of those. And for a long time, I thought that was the point of Tohoku. That was the point of it for me, is, oh, that's where you go to learn, that you've always got that under certain plausible conditions, which have been mentioned, and I'll come back to very briefly, all your group objects always have injective resolutions. Now, ad hoc proofs of this had been known for some cases before Grothendieck published this very general proof. Before, in his mind, motivated this, what is a 120-page paper. But actually, the general case was not known for topological sheaves. Grothendieck proves, I think for a lot of people at the time, this was the key result. Grothendieck proved that every sheaf of abelian groups over any topological space has an injective resolution by sheaves over that space. This had not been known before Grothendieck, and in fact, Serre doubted it. Serre thought this won't work if the space isn't suitably separated. And you certainly couldn't, if it was true, you couldn't expect to prove it because it's too crazy a claim. I mean, it's hard to prove a claim that all the evidence suggests couldn't be true anyway. But it didn't suggest that to Grothendieck. And Grothendieck's proof used transfinite induction, but we're not talking some transfinite induction. We're talking about transfinitely many Alepps, unless it's transfinitely many bets. I don't remember, because I do not live without the generalized continuum hypothesis. I understand, but I don't. So we're talking infinitely many successively larger infinite cardinals. And you know, when one infinite cardinal is larger than another, it's not a little bit larger, right? It's incomparably larger. It's as much larger as it is itself large. So there he got, and so he's got to use unboundedly large cardinals. And it was brought up, I think, Jean-Pierre, you were saying that his proof is more elegant than Buchsbaum or MacLean. And I think the reason, I thought this while I was listening to you, I thought this because of Jean-Pierre's talk. The reason it's more elegant is that Buchsbaum and MacLean were both generalizing a result by Baer on modules over rings, just plain modules. Baer had proved this over any ring, every module has an injective resolution. It's trivial that abelian groups have injective resolutions, but he does it for modules over any ring. Buchsbaum and Baer both saw we need to generalize this, so they set out to generalize. But Grothendieck does not generalize it. Grothendieck strips it down. Grothendieck says, let's not come up with a more involved idea that will have the applications we want. Grothendieck says, let's drop the assumptions that block it from applying in the cases we wanted it to. And that's why it's more elegant. He's reducing Bayes' proof to the truly relevant facts. Well, as a historian of math, I want to say, well, how do you know those ones are truly relevant? I mean, it's some nice reduction, it's okay. But Grothendieck has an answer, because 5 years later, when I invent Topos, this works exact. It's the right way to do it. But there were also various constructions using universes in the SGA, especially SGA4, so much SGA3 or but in SGA4, and also in categorical logic that Grothendieck began in the Kansas paper of 1955. I don't have to, and developed in Buffalo in 73. Now, Fernando pointed out this universal algebra being done in the 80s using higher categories and all. And at first I thought, well, that wasn't, no, but the Kansas one isn't that. The Kansas one isn't universal algebra, it's just categorical algebra. It's very elegant, but it's not what he's going to do in the 80s. But it will involve, toposes in higher categories. And it's going to involve the universe construction. Well, we'll get to it. And I think the lesson to get from this is that for Grothendieck, if a technique works, there should be a reason it works. And you should be able to find that reason. And if it seems like, oh, this is so trivial, it's not worth finding the reason, then one of two things is the case. Either there's a trivial reason, great, find it out, or you were wrong that it's trivial. One way or the other, you should find out why it works. And that's what he means when he says there's mathematics behind this. We'll get back to that quote, but if a technique works at all, either it really is super lightweight and you could explain why in a sentence, or there's something to it and you should explain what there is to it. Now this gets us to another aspect of Grothendieck on identity, a much more theoretical aspect than what Kevin was talking about. What Kevin's talking about for machine implementation, really crucial. This stuff is not machine implemented right now, to my knowledge. No equivalence of categories encountered in practice is an isomorphism. I won't even attempt it in French because we've been hearing French words pronounced in good French this morning. So Grothendieck introduces this idea of equivalence of categories. As Jean-Pierre says, this was an idea that was not available to people before Grothendieck and was a major obstacle to Bourbaki taking up category theory, because frankly, the tools that we would now use to do what they were doing didn't exist yet. But I like what he says right after defining equivalence. He comes and says, it's important to observe, okay, yeah, this is still in the Tohoku paper. It's important to observe the difference between this notion and the stricter notion of isomorphism of categories, which applies if we wish to compare categories that are sets. Okay, so categories, we would not be category theorists if the things we talk about didn't have morphisms between them, right? The morphisms of categories are functors. But the morphisms of functors are natural transformations. So categories are isomorphic if there's functors between them that cancel each other out on the nose. This composite is the identity. You might as well have stayed here. That composite is the identity. You might as well have stayed. But another thing that can happen is this composite is not the identity, but it's functor isomorphic to the identity. And this composite is functor isomorphic. It might be one of them is the identity, the other is not. Or in general, neither of them is the identity, but they're both functor isomorphic to the identity. And he wants to say that that's what we actually find in practice. When you're proving a duality theorem in general, when you're proving some particular, verifying some construction of toposes, you're going to do it not in general. You're going to say, I've got this category, I'm going to build this other category, they're the same, but they won't be isomorphic in general. In general, there'll be a pair of functors between them where the composites are isomorphic to the identity. And this is good. What it means is everything that happens here described up to isomorphism, the same thing happens here up to isomorphism. And since we were only talking up to isomorphism, that means everything that happens here, the same thing happens here. But not because the functors are inverse to each other, the composite functors. Well, functors are inverse. So it's important to observe the difference between this notion and the stricter notion of isomorphism, which applies if we wish to compare categories that are sets. And that I do not have a nice cold explanation for. There's something to know about it, but it's a little bit puzzling. The keywords that I do want to stress here are encounter and difference. We don't only encounter categories or functors, we also construct them. And the ones we construct very commonly are defined up to isomorphism. It's just, it's convenient to be able to do that. The ones we encounter will almost never be isomorphisms. But often the ones when the construction is specified up to a unique isomorphism. And also difference, well, he's saying you need both terms. Now there are programs in category theory to do everything up to equivalence, which is great. I mean, it's a fantastic thing to work on, but it's not what Grothendieck is doing here. And you might make a case that it's more of what Grothendieck is doing in the 80s. And I don't know, I haven't looked into it from that point of view. But Grothendieck on this kind of evil, he says, all the better. If you can get an isomorphism in categories, I don't object, of course, all the better. If you get an isomorphism, good. Now you won't in general. If you can, and he gives examples, subtopoi. We have a topos, it's a category, think of it as a category of sheaves on some space, although this space probably doesn't exist in any other form. We probably don't have no other description of that space, but he's going to tell us repeatedly in Buffalo, think of it as sheaves on a space. And then you have a subtopos, which could be like sheaves on a subspace. He says, I don't distinguish between two subtopoi that are equivalent subcategories, but it's not for the reason you might think. It's that he never considers any that aren't full subcategories. He doesn't consider other ones equivalent to the full subcategory, strictly full subcategory. And that's normal. The sheaves in a subtopos have a certain universal mapping property compared to a topology on that topos. Anything that's defined by universal mapping property is already defined up to isomorphism. So you're naturally going to take the category of all the things that have that property. The only different equivalent categories would be subcategories of that. Why would you take a subcategory of all the ones there are? It's just easier to take all the ones there are. He's explicit. An open subtopos has a closed complement that is constructed on the nose, not even up to isomorphism. It's constructed up to identity. It is the closed complement. Compositional morphisms of topoi. Oh, this is fun because it shows you how he's thinking. This is in lectures in Buffalo. He's explaining to people. Okay, he has gone to Buffalo, 1973. SGA4 has just appeared in print. We're now talking, what, 11 years after it happened, well, maybe 10 years after it happened, it's finally come out in print. He's in Buffalo where people are not as up to date as people in Paris. And he's going to, originally, these lectures, they were scheduled for 10 hours. He was going to give a 10-hour introduction to the theory of topos in SGA4. And with being Grothendieck, it starts developing. At hour 12 and a half, he says, oh no, we've come to the end and I haven't really told you anything about topos. I think that I need at least one more session to tell you what a topos is. And it would be good to have a couple sessions after that. So now then he expanded to a 15-hour session. And what we now have, through Michael Wright's efforts, 33 hours of digitized tapes of the lectures and then workshops on the topic. Some tapes that can't currently be digitized, or couldn't, I don't know. So what he's saying to these people who he knows they like him, right? I mean, you don't get invited to talk to a math department with people they don't, but he also knows they're not really, they're not up on this the way people in Paris are. So he's talking about morphisms of topos. A morphism of topos is, among other things, an adjoint pair of functors The morphism goes from this one to that one, but it has an adjoint the other direction. So then you're going to compose them. Well, this is composition of functors. He says compositional morphisms of topoi. He uses topoi. This is related to a terrible tragedy of the Buffalo lectures. Grothendieck is really determined to speak American English when he's in America. You can see this. He talks briefly about espace tale. Well, he talks about espace tale, not briefly. And he talks briefly about étal morphisms. But because he's in America, he says étal all the time. It's espace étal morphism. The pronunciation does not change. And this is the delight of listening to tape recordings. You're constantly hearing click, 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 click. As I wrote here, I hope he reads it aloud, and he doesn't. But he's saying to them, compositional morphisms of topoi is so he uses the American plural of topos, the usual common. It's clearly associative on each of its components. He's the one that goes backwards and the one that goes forwards. And then he says, well, it's associative up to isomorphism. And then he says, oh, but the isomorphism is the identity here. Never mind. He uses never mind a lot. Just cut things off. I don't know if those people on Saturday Night Live took it from him. And he ties equivalence and isomorphism to the universe problem. Because I mentioned this before, but didn't go back to it. It's important, however, to observe the difference between this notion of equivalence and the stricter notion of isomorphism, which applies if we wish to compare categories that are sets. By sets here, he means small. And I would tell you, the first 22 times I read this, I thought, oh, discrete categories. Sets are discrete categories. But no, that's not what he means here. What he means here is small. And one of the ways you can, okay, today we often call a category a set to mean it's discrete. It's a category with only identity arrows, so you didn't need to call it a category if you didn't want to. You didn't want to. But in 57, he used set only to indicate small size. And in fact, as a technicality, to mean there's a set of all objects. It does not require that there be a set of all morphisms. Again, Mike Barr, who's been mentioned before, noticed that in his translation. And the example he gives is all set size indiscrete categories. And there's a reason he wants to say indiscrete, because he wants to say they're all equivalent. No matter how big a set-sized category is, if every pair of objects is linked only by one pair of arrows, from which it follows that these arrows are isomorphisms inverse to each other, it's equivalent to any other one like that. But they're isomorphic only when they're equal in cardinality. So his example of the difference between equivalence and isomorphism pivots directly on the question of what's a set and what's a proper class. Because cardinality or even bijection of proper classes is a much knottier foundational problem than cardinality of sets. As soon as you have the axiom of choice, every set has a cardinality in the most classical strictest sense. Bijection of proper classes, it's not that it isn't understood. Bijection of proper classes, perfectly well understood by specialists, but it depends on foundational details that you really don't want to worry about. I mean, we sometimes say if you don't assume an axiom of constructibility, when what we meant to say was if you deny the axiom of constructibility, right? Because merely not assuming it doesn't prove it's false, right? And lots of classes that are clearly in bijection, if you do assume constructibility, might not be if you don't. And he links this in a way that I do not know how important this is for anything, but I do know it's what's going on here in his thinking. But then he gets more into the meat of it. Oh, part of the reason I left this label in, when you see this is number 2, what that means it's from the originally scheduled series. After the first 10 lectures, they start putting the date of the lecture instead of the serial number. Sometimes it's technically necessary to replace large categories by smaller subcategories, which are small in the sense that objects and arrows for really a true honest set. This is 1973, so he's not saying exactly what he said in 57. He now includes the arrows have to be a set also. Really form a true honest set. Sometimes you have to do that. This, of course, he says, is kind of unpleasant because one likes to look at any category, whatever, as being a structure on two sets together with two arrows and a third composition arrow. That is, you've got a set of arrows. It has a domain arrow to the set of objects. It has a codomain arrow to the set of objects. From a certain pullback, there's a composition arrow. That's what the way he's using this here. So we got a domain arrow, codomain arrow, composition arrow. This is all of arrows of whatever category we're talking about. The only handy way out, which I know of, is to use a setup of universes or something equivalent to it, which gives a certain hierarchical structure nonsense like higher and higher order cardinality sets. I don't want to go too much into this, he says. I will say that through these lectures, he frequently refers to category theory as abstract nonsense. He likes calling it abstract nonsense. This is one hint that that phrase is not to be understood as an insult, right? It's a phrase to put things in perspective. It's to say, right now, I'm not telling you geometry. I'm telling you abstract nonsense, which in this case will yield a geometric fact, or I'm not telling you algebra or whatever. And this is still in the scheduled lectures. He's saying I don't want to go too much into this. Then in June 20th, so now we're beyond the scheduled lectures. And we're into what he really wanted to talk about. The reason he scheduled a lot more of these. He's interested in the idea of classifying topos. Somehow, every algebraic structure should have a classifying topos. The problem is he doesn't know how to define algebraic structure yet. And contingent on exactly how you do that, he's not dead sure how you'll define classifying topos. Those are the key ambiguities. What do we mean by algebraic structure anyway? So there should be a one-to-one correspondence between algebraic structures up to a certain notion of equivalence and topoi up to a certain notion of equivalence. I don't know how certain he was. In everything he says, equivalence of topoi is categorical equivalence, except you've got an adjoint pair of functions, but still equivalence means categorical equivalence. In everything he says here, all of his talk of two categories is the strict two category of one categories. That's the only thing he's doing here, which is not the only thing he'll be doing in the 1980s. And I don't know, does he really believe that's what he wants to do here? Has he not questioned whether that's what he wants to do? Is this just the best he can do for right now? Did I mention this is 33 hours of tapes? I've only listened to it once, through start to finish. It will repay more. It will repay more study. He says size can really make problems for existence of universal things if these diagrams are not really sets. But for the time being, let's forget about it, which is a perfectly good research perspective. You know, we'll bring that up when we need it. You know, we'll ignore it. But I can tell you, when I had my sabbatical at Harvard, and when people heard that I used the term category theory with no expressions of disgust, what they assumed I meant was I love to talk about the size of diagrams. I'm constantly obsessed with how big colimit diagrams are or limit diagrams. That's what category theory means. I think to a fair approximation, what category theory means to most mathematicians now is it means you're worrying too much about categories and functors. If you weren't worrying too much, then what you're doing would be algebra or topology or whatever you think you're doing. It's when you're worrying too much about it, then it's category theory. Although I had a great experience walking along on campus. This is about 10 years ago. And I meet this new mathematician we just hired. It's a woman, she does modeling. You'll never think what she was modeling. She was modeling Arctic char migrations around Iceland. Now, I'm very fond of Arctic char, so I thought this is pretty good. She does modeling. She does mostly. She uses graph theoretic language. And so great. I'm interested in everything, especially if it's Arctic char. And she asked, "Well, what do you do?" And I said, "Oh, I'm in philosophy. I do philosophy of math." And she looks at me. She's a nice person, you know, but why would philosophers want to know about math? And I said, well, for instance, one interesting question to a lot of philosophers now is, how can mathematicians work with abstract structures without ever saying what they're structures of? And she says, oh, that's easy. It's called category theory. This woman uses no category theory in her work. I mean, John's trying to change this, right? I mean, but she
give me her email.
Well, she's in Amsterdam now. Yeah. She never uses category theory, but she goes to math meetings, and she, unlike most of our philosophical colleagues, knows that if you go to a math meeting and someone's talking about abstract math, they're likely to say category or functor or both. So I loved when she said that, but I still think that to most people, well, even to her, category theory meant something that a philosopher might want to know about. But it's just like set theory. 99 times out of 100, if a mathematician talks about set theory, they mean something independent of the FC. You don't call it set theory if it's just about sets. You call it set theory if you need to know independence proofs to understand the status of it. Same with category theory. You don't call it category theory if it's actually good topology. And I will say, absolutely typical expression in these tapes, and other people have mentioned Grothendieck saying this kind of thing. He's trying to formulate something. He spends a lot of time formulating things he's not sure how to do in the workshop session. Like I say, he does not yet know what he's going to mean by algebraic structure. There's paradigm cases, of course. Lots of categories of rings that he encounters. Those are algebraic structures. But he doesn't know in general. I'm guessing there must just be one way to write this. There can't be two ways. If it's a good question, it should have a clear, unique answer. And every important topic is made of good questions, but they do have clear, unique answers. I'm guessing there must just be one way to write this. There can't be two ways. And somebody actually asks him, Jack Duskin, if you know any of the historic names of Buffalo category theory, asks him, when you're doing your algebraic geometry, do you ever run into a problem where there's two ways to express some classical concept in categorical language? And he starts out by saying, well, yes, that could certainly happen, because lots of simplifications that work for sets don't work in general. So two things that look equivalent over sets might not be. But he says, but no, really, no, there's never been two ways to express something in my experience. Now, this is not a theorem. This cannot be technically true, but it is his experience. And then we come to where he lingers on universes. And by the way, with respect to universes, I like these quotes, so I'm getting, there's an idea of Samuel's, Pierre Samuel, which has never, I think, been really looked at carefully. There's a little trouble with universes, because in order to be able to work with them, one who has to add such a strong axiom to set theory about existence of universes, you have to say they exist. And this turns out to be a strong axiom. Once one adds the axiom, one is in a way happy, because one has a lot of leeway in order to do category theory. Now, if you spend much time on the FOM email list, you know that some people are not happy at all when you add universes. But Grothendieck was happy once he had universes. For instance, Deligne has just proved, it seems, he just got the letter the day before. Deligne has just proved, it seems, a beautiful theorem based on lectures. And I guess he's used large cardinals, all the formalism on état cohomology. He's talking about Deligne's proof of the last Bay conjecture, which was delivered at conferences. I forget who these, Hodge or somebody. conferences in Cambridge. He's just gotten a letter saying Deligny approved the last of the Veil conjectures. By my count, that's 4, but some people count 3. I'm pretty much convinced that he could not do without the état cohomology. And now you have all these topoi, all this general nonsense, and you have to have universes. Now, at this point, he does not know Deligny's proof. And if you know the story, you know that Deligny did not follow the strategy Grothendieck dearly, dearly wanted. Grothendieck had a particular strategy to prove these conjectures. The last Veil conjecture will fall out as a triviality from there. Deligny doesn't do that. But he does use état cohomology. It's not that he used a lot of état cohomology, but for the last Veil conjecture, he doesn't get this incredibly sweeping result that Grothendieck wanted. And that people have been working on since. And when Pierre Cartier would talk about this, you'd say, look, the people that will say they've been working on this for 30 years now, they haven't proved it Grothendieck's way. And I think that's because the conjecture Grothendieck wanted them to prove is probably just not true. That, of course, would give one explanation for everyone failing to prove it. But at any rate, Deligny didn't do it that way. It hasn't been done that way since. But Deligny certainly did use état cohomology. And people are sometimes misled by SGA 4.5. Deligny publishes SGA 4.5 and says, look, for these proofs using état cohomology, there's a lot of SGA 4 that you don't need to know. Really, if you'll just take it on faith. He does specify take it on faith. He doesn't say there's a lot you never needed to hear about. He says there's a lot you don't need to know if you'll take it on faith, because it's a lot like cohomology of topological spaces, more like cohomology of complex manifolds. So you don't need that. But Deligny never suggests you don't use état cohomology. He does use état cohomology. I'm pretty much sure. So now you have all these topoi, this general nonsense. You have to use universes. Deligny does specify you don't have to use universes. What Deligny is saying there is technically quite right, and everybody knew it from the start. You could avoid the whole language of Topos. And Deligny has said in Quelques idées maîtresses dans l'œuvre d'Axiom of Grothendieck, which last time I tried to speak French and some people didn't always understand me. Quelques idées maîtresses, master themes of Grothendieck's, in Grothendieck's work. Deligny will say, you should think in terms of Topos. It's a great idea. It's one of his greatest ideas. Think in terms of Topos, but you don't need to use it in your proofs. Because in your proofs, you can go down to the site of each topos you're interested in. These sites will always be very small. Grothendieck makes this comparison often in Buffalo. The category of sheaves on a topological space is a proper class-sized category. It's a huge category. The topological space is just a little set. And Deligny says this about the sites used in algebraic. The site is little. The category of all sheaves on it is big. And Deligny is interested in the category of all sheaves on it, but he's not interested in collecting that category into one set. So he doesn't need universes. But Grothendieck is saying, so you have to use universes, but it's an exceedingly strong axiom on sets. Even if the traditional theory of sets is non-contradictory, it is possibly contradictory if you add an axiom like this. I mean, Grothendieck is interested in logical foundations of mathematics. It's not the thing he's most interested in, but he does care to get it right. And Jack Duskin says, but isn't there some kind of relative consistency proof? And Grothendieck says, no, 10 years ago or so, when I came up with this intensive use of universes, he didn't invent the idea. Tarski had this idea in the 30s, but Tarski didn't use it to define any cohomology theory, let alone état. I asked a few logicians, and they seem to be convinced that it's a very strong axiom. There's no hope of proving relative consistency. Here we get an upper bound on Grothendieck's sophistication and logic. He cares. He wants to know these things, but he does not say, oh, I remember if a universe exists, that proves consistency of ZFC, and by Gödel's incompleteness theorem, that assumption can't follow from ZFC. He doesn't think to put it that way, but that's, of course, what all the logicians told him. And what he retained is, yes, this is a genuinely stronger assumption. You're not going to get rid of it. There's no relative consistency proof here. Also, remember, this is 10 years after he asked the logicians. I mean, I don't know what he made of it when he was talking about it with them, but 10 years after, he doesn't remember that it's that clear a connection, but he does remember the conclusion. But Samuel, he thought about introducing galaxies that are universes that are kind of small, you see. Samuel already, back in 1963, is saying, maybe we don't need this whole axiom of universes. Now, they went with the axiom of universes because they had it on hand, and it wasn't fought over like the set theory volume of Bourbaki was, but they go with it. They've got it. It works. It has Tarski's name on it. I don't remember if they ever mentioned Tarski. They use it. But Samuel, I thought, you make all the axioms of universes, except that the axiom involves the union. I won't go into this because Grothendieck's description here is almost certainly wrong. It's either wrong or completely unclear. On the most natural construction of what Grothendieck says here, it's an alternative description of universes. It's not weaker than universes. But then he comes down to his observation was that in most cases, when we need this axiom of set theory, we can take unions of sets. Now, I don't get a lot out of him saying unions of sets there, but it says, in most cases, we kind of know that the sets we want to get are already contained in an ambient set. That's the more meaningful part here. Grothendieck is saying, Samuel discovered that most of the time, when you're going to use a universe to show that some set exists, there was actually a smaller ambient you could have used. This is a fact about most of the time. Most of the time, you didn't really need that because there was something smaller. So he proposes to call a galaxy something which satisfies this axiom. So instead of this, we make the weaker assumption. At least either it can be shown that these exist, or it can be shown that their existence is not inconsistent with the other set theory. Grothendieck is not really, he doesn't remember it very clearly because it was 10 years before. And, you know, Peter Schultz has been working on this lately. Peter Schultz, for various reasons, wanted to invoke a construction that used arbitrarily many stages of universes. He's an interesting guy. He's interested in all kinds of stuff. He said, well, did I really need these to be universes? He says, no, I didn't. These could have been much weaker kinds of cardinals. I could actually do all of this in ZFC by tailoring my steps instead of just saying, take the next universe, take the next universe. I'll specify a next step that provably does exist, and then a next step after that that provably does exist. And this is what I did systematically in the review of symbolic logic. What, to me, the answer I liked for this problem was, you look at all of Grothendieck's math, and you can see something that no one could have known at the time. You see that none of it uses the axiom of replacement. You never need replacement. Now, while the work is in progress, nobody knows. We might need replacement tomorrow, right? Well, tomorrow hasn't come yet. But now, when you can look back on it, you can say, look, 3 decades of this stuff never used the axiom of replacement. We don't need models of ZFC. We can get by with models of Zermelo set theory, and better than that, with bounded separation, we can get by with models of Laubier's elementary theory of the category of sets. That's all we need. We don't need universes because, for example, with the injective resolutions, he's going to take a group, he's going to give an injective resolution of it. Following Baer, he keeps saying, take the next cardinal, take the next cardinal, take the, and you don't know how many times you're going to have to take the next cardinal. So you don't know, so you can't bound it. But if you look at the proof more closely, you can say, oh no, I only need maps from the natural numbers. I only need sequences of constructions that I can do in this set, which means I just need the function set from the natural numbers into this set. I don't need to keep taking successive cardinals. I can take a pretty big product of sets, big in the practical sense. It's got like 3 factors, which you normally don't take a product with 3 factors. You take a product and then take a function set from the naturals to that. You can do the whole construction inside there. You didn't need to keep going to larger and larger cardinals. We can see that now. They couldn't see it then. And what that means is universes model ZFC with replacement. You were nowhere near needing to model replacement. People don't always know how radically far replacement is from most of mathematics. It's a good trick to find results that actually need replacement. For example, Harvey Friedman, one of the first things that made him famous was discovering that a certain determinacy result in set theory that had been proved using replacement needed to. Yeah, that was, everybody said, we can't do without it. We've got to prove with it. Harvey comes along and says, here's why, because you need it. And that's hard. There aren't a lot of results that need replacement. So I think, but here's the problem with my fix. My fix, if you wanted to get just on the level of Laver's set theory or what's called simple theory of types, if you do proof theory, to get it at that result, I get 1 universe that way. If you want 2 universes, I have not worked that out. I'm not sure how much stronger my kind of approach would be. Right. I mean, because we are talking about a kind of approach. Maybe I didn't see a way to do it cheaply, but you could see a way to do it cheaply. I didn't even look, so I don't know how cheaply I could do it. But Peter Schultz, he does want to do it arbitrary finite numbers of times. Also the homotopy type theorists. And they'll talk about this. They'll say, honestly, I don't know how many of these I needed, but I thought I might need some. Jacob Lurie says it in print in his book. And it hasn't been a priority. It hasn't been a research priority, and there's no reason it should. Bringing me back to that title, I do not mean to suggest that universes are of comparable importance to topos and schemes, but it's a legitimate subject. Because Grothendieck didn't pursue things that weren't legitimate subjects. I mean, we're all fallible, but basically didn't. I don't remember. He's not really sure what these alternatives was. Of course, one has to be very careful in a certain number of existence theorems. For instance, when one constructs injectives, I can't tell you how happy I was when I heard that. Yay, injectives. I said that was where you need it. He said so too. Yeah, because it's true. And Charles Weibull had already seen this also in his homological algebra. But what Charles Weibull did, like a lot of people, Saul Pfefferman, he showed that you could do something like the Grothendieck techniques within Zermelo-Frankel without universes. What I've showed is you can do them in Zermelo set theory. In fact, bounded Zermelo set theory is hugely smaller. Knowing you could do it in ZFC, everybody already knew you could prove all these things in ZFC. You'll see online people still ask, can the proof of Fermat's last theorem be given in ZFC? Everybody who was involved in building the Grothendieck techniques knew from the start that anything you could prove this way in number theory, you could prove in ZFC. That was never, ever a question. But ZFC is already, people in number theory don't really use ZFC. I mean, that is, they use 0% of the strength of it. And they use 0% of the complexity of it. But what you can show is when you look at it, you can construct those injectives in, if you like to, finite order arithmetic. In logic, you have natural numbers, sets of those, up to any finite level. You don't even say every finite level. You just say up to any finite level. And you can get the result on injectives there. Most of the results that Grothendieck school uses are transparently far weaker than that. None of them are stronger than that. But I wonder whether that would be enough, you see, to do most of what one does in homological algebra and étale cohomology, for instance, and such things. I want to advocate that sense of wonder. Yeah, he wonders. He knows. I've got two fixes here. I could have told you that I didn't mean anything I said about Topos, it's all ZFC, or I could have told you use universes. Either one works. But can I do something more elegant that's more to the mathematics? Because if there is mathematics here, of course, it's being hidden if your assumptions are radically stronger than you needed. Can we strip down the assumptions and discover the mathematics? Like I was saying, I think the reason his proof of injectives is more elegant, his whole theory of the Billian categories is more elegant than Bayes or McLean's, is he doesn't think, I'm going to generalize this to a bigger case. He says, I'm going to strip this down to get rid of the complications that prevented applying. You see, practically, when one works with Topos, with categories, and one wants elbow room, one goes only 2 or 3 steps higher. At the most, you see, one has the feeling that if one allows sets of cardinality 2 to the 2 to the 2 to the C, for instance, okay, he says those words, so I know that's one has already enough leeway or still more leeway with Aleph naught exponentiations. Maybe it's possible. You see, galaxies are perhaps the right thing. I don't know. Well, he doesn't even remember the precise definition of galaxy. But I want to advocate that as a this is one sense behind Cartier and Benabou saying that Grothendieck did not care about universes, he cared about Topos schemes. Okay, he's very happy to consider an alternative to universes. In fact, he advocates people should look for alternatives to universes. He's never suggesting alternatives to Topos or schemes. No, those theories are good. Those theories are good right now. The theory of universes is good for right now, but those are good. I don't know. Yeah, he does. Well, I won't even go into that right now. So then he says, it's kind of nice that the veil conjectures are true. I mean, really, he spent a long time pursuing this, and now he's heard that Deligny has proved the last one. And without giving an introduction to veil conjectures, the last one gives you all the others. You can either say it builds on all of them or it gives you all of them. The last one really caps it off. It's not like there's 4 problems and first one got solved. No, the last one really covers all the others. And someone asks, well, wait a minute, are they proved or do they still depend on the existence of universes? Grothendieck says, that's the worst joke I ever heard. I just got a letter from Illizy telling me that Deligny proved it and was explaining in all details the proof in Cambridge at a seminar, oh yeah, in honor of Hodge, one of the most beautiful theorems ever proved. And the voice, these are tape recordings, there's no attendance list. I don't recognize his voice at all. What is the joke? And AG says, the joke is that I'm thinking it's quite clear he will have used a tau cohomology, and a tau cohomology, after all, means we've added all the theorems of Topoi. Okay, this is not an uncontroversial statement. In fact, Deligny has already told you you don't need them, but remember that in Deligny's case, he does say also you should know them. You should think this way, but you don't actually need them. It's just that one has the feeling that there's some hard core, you see. A tau cohomology, I mean, it's computed, and there are very precise things about it. That's the hard core. All these categories, universes, et cetera, are some kind of focusing around. I have to admit, I'm not sure of the word focusing. It could be fussy, and I wasn't sure. These things are some kind of focusing around in order to make the parcel, you see, more appetizing. It's something like a psychological pointing or oil or something. And somebody says, in order to sell the product. And Grothendieck goes on that. I think it's just adorable at a meeting where a lot of us do Topos theory to be told that you add in the Topos to make it more appetizing. But for Grothendieck, yes. Grothendieck, absolutely. That makes it what it is. Okay, well, I guess that's what I got.